All right, let's get into what has to be one of the greatest scientific showdowns of all time. I mean, this was way more than just an argument between two geniuses. This was a battle for the very soul of physics, a duel over what reality is. In one corner, you've got Albert Einstein, the man who gave us relativity. And in the other, Niels Bohr, the pioneer of the quantum world. Believe me, their epic clash would shape physics for the next century.
So what was this big fight all about? Well, it boiled down to two completely opposite ideas about how the universe works. Einstein, he believed in a tidy, clockwork universe. You know, a reality that's out there, fixed and solid, whether we're looking at it or not. He famously said, "God does not play dice." But Bohr? Oh, he came along with this wild new idea. He said that down at the quantum level, reality is, well, it's blurry, it's based on probability, and it only becomes real when we actually measure it. In his view, the universe absolutely does play dice.
Okay, so to really get what they were arguing about, we've got to take a quick look at the weird new rules of the quantum world that Bohr was defending. This whole set of ideas is known as the Copenhagen Interpretation.
First up is something called wave-particle duality. And yeah, it's as weird as it sounds. Physicists found that tiny things, like an electron, can act like a solid little pinpoint particle, but they can also act like a spread-out wave. Now think about that. A particle is in one specific spot. A wave is everywhere at once, so how can something be both? Well, quantum mechanics just sort of shrugs and says, yep, it is. But here's the catch. You can never see both sides at the same time. It's a fundamental paradox right at the core of everything.
And then there's the Heisenberg uncertainty principle. Now, this is crucial. This isn't about us having bad measuring tools. Bohr said this is a fundamental law of the universe. It means you can know a particle's exact location, but if you do, you have no idea how fast it's going. Or you can know its exact momentum, its speed and direction, but then its location is a complete blur. It's like a cosmic seesaw. The more you know about one thing, the less you know about the other. Nature literally won't let you know both perfectly at the same time.
And right here, this is where Einstein just said, nope, I can't accept this. The idea of a universe built on chance, where reality is fuzzy until you look at it, it just went against everything he believed in. He was convinced there had to be some deeper, hidden reality, a more complete theory that would bring back that beautiful clockwork order. And that famous quote, "God did not play dice," man, that says it all.
So what does a genius do when he thinks a new theory is wrong? He tries to break it. Since he couldn't do it in a real lab, Einstein used the most powerful tool in his arsenal, his own imagination. He came up with these incredible thought experiments, each one a precision strike designed to find a logical flaw, a crack in the armor of quantum mechanics. Okay, his first big attack was at the legendary 1927 Solvay conference. He proposed a super clever twist on the classic double-slit experiment. So he said, imagine the wall with the two slits is on wheels, or rollers, so it can move. The idea was, when a particle zips through one of the slits, it would give the screen a tiny little nudge. By measuring that nudge, or recoil, you'd know exactly which slit it went through, you'd see it as a particle. But you could still look at the back wall and see the interference pattern, which proves it was a wave. See what he's doing? He's trying to trick nature into showing him both sides of the coin at the same time. But Bohr, apparently after a whole sleepless night thinking about it, came back with a brilliant rebuttal. He pointed out that to measure that tiny little kick on the screen, you have to know the screen's momentum with incredible precision. And what does the uncertainty principle say? If you know the momentum precisely, you have to lose all certainty about the screen's position. And that little bit of fuzziness in the screen's position is just enough to completely wipe out the wave pattern on the back wall. The act of measuring the particle path completely destroyed the wave evidence. A perfect counterattack. Round one goes to Bohr. But Einstein wasn't done. Oh no. In 1930, he came back with another, maybe even more clever attack, the clock in the box. Imagine this. You have a box filled with light, hanging on a super sensitive scale. Inside, there's a clock connected to a tiny shutter. The clock opens the shutter for a split second, letting just one single photon escape. So Einstein argued you could weigh the box before and after to know the exact energy of the photon that left, right? And the clock tells you the exact time it left. Boom! You've just measured both energy and time with perfect precision, which should be impossible according to the time-energy version of the uncertainty principle. Now, legend has it this one really stumped Bohr for a bit. He was genuinely worried. But then he had this incredible breakthrough. And you have to love the irony here. He used Einstein's own theory of relativity to save the day. Bohr realized that to weigh the box itself has to be able to move up and down in a gravitational field. But what does Einstein's general relativity tell us?
that gravity actually slows down time. So the unavoidable uncertainty in the box's vertical position creates an unavoidable uncertainty in the clock's timekeeping. It's just perfect. A total checkmate, using Einstein's own greatest discovery against him.
So, after being defeated twice, Einstein changed his whole approach. In 1935, he teamed up with two other physicists, Podolsky and Rosen, for what would be his final and most powerful challenge. This time, he wasn't going to say quantum mechanics was wrong. No, he was going to argue that it just wasn't the whole story, that it was incomplete.
The whole thing centered on this incredibly strange quantum link that we now call entanglement. So imagine you create two particles that are linked together, and they fly off in opposite directions. Quantum theory says that if you measure something about particle A, you instantly affect particle B, even if it's light years away. To Einstein, this was just nuts. It was faster than light communication, which his own theories forbade. He came up with a great name for it. He mockingly called it spooky action at a distance.
Okay, so here's the logic of this EPR paradox, step by step. Let's say you measure the exact position of particle A. Because it's entangled with particle B, you now know the exact position of particle B without ever looking at it. But what if, at that exact same instant, your friend across the galaxy measures the momentum of particle B? Well, because of that spooky connection, you now also know the momentum of particle A. So think about it. You've just figured out the exact position and the exact momentum of particle A at the same time without ever laying a finger on it. That completely shatters the uncertainty principle. For Einstein, this was it. This was the slam dunk. The only way this could possibly work, he argued, is if the particles had their properties, their position, their momentum, locked in from the very beginning. They were always there, we just didn't know them. He called them hidden variables. So quantum mechanics wasn't wrong, it was just blind to this deeper reality. The universe wasn't spooky, it was solid and predictable, just like he always thought.
And for decades, that's where it stood. It was just a brilliant philosophical argument, a thought experiment with no way to actually test it in the real world. The final answer in this great duel wouldn't come from another genius mind, but from an actual experiment. And sadly, it would happen long after both Einstein and Bohr were gone.
So the paradox was proposed in 1935. It wasn't until 1964, almost 30 years later, that a physicist named John Bell came up with a brilliant mathematical theorem, a way you could actually test this in a lab. But even then, the technology just wasn't there. We had to wait until the 1980s for a physicist named Alain Aspect and his team to finally build a machine sensitive enough to get the answer.
And when the results came in, they were just mind-blowing. The experiments proved over and over again that the universe violates what we now call Bell's inequality. And what that means in plain English is that Einstein was wrong. There are no local hidden variables. Those particles do not have their properties set in advance. They are genuinely undecided until the very moment one of them is measured. That spooky connection, it's real.
So, in one of the greatest ironies in the history of science, Einstein's ultimate weapon, the very thought experiment he designed to finally prove quantum mechanics was incomplete, well, it ended up paving the way for the real-world experiments that proved his own worldview was wrong. It turns out, the universe is spooky. Bohr was right.
And you know, this really gets to the heart of their lifelong disagreement. It was a philosophical difference. Einstein's quest was, well, you could call it ontological. He wanted to know what the universe is, fundamentally. Bohr, on the other hand, his quest was epistemological. He was focused on what we can know about the universe. And in the end, reality itself, through experiments, sided with Bohr. It seems the universe is defined by what we can know about it, not by what we wish it was.
Einstein's stubborn refusal to accept the weirdness of quantum mechanics forced us to actually test it, and the answer we got was stranger than he ever could have imagined. It really does seem like the universe is waiting for us to look at it. Which leaves us with this incredible, haunting question. If reality only snaps into focus when we observe it, what is it the rest of the time?